Hello everyone. Today, I will provide a basic overview of masonry wall modeling in the SDA program. Masonry wall is modeled with panel elements. In the SDA program, panels can be modeled as wall elements by defining brick material properties. The panels consist of finite elements with brick wall properties. I will model a single-story example of a masonry wall structure in the program. And as I mentioned at the beginning, I will be using panel elements while modeling. I will show the modeling of a few panels for example purposes, and then demonstrate how to define them as masonry wall in the program. Now we come to the beam information section here and select the panel option. The panels will be 30 centimeters wide, and from here I start modeling my panels. When modeling panel elements, they should be modeled from axis to axis, and each subsequent panel element should be named differently. So, it is not correct to model a single panel element from start to finish when modeling, because each of the panel elements here represents a separate wall. Therefore, the modeling should be completed at the intersection points, that is, at the axis intersections, and then proceed to model the other panel. Yes, we can perform our modeling in this way. Yes, I quickly completed the modeling. This is the final state of the model. The panels were defined using the same logic. We also defined our slabs in between. The feature of our slabs is as follows. We used a 12 centimeter thick slab. I set the live load to 0.2 tons per square meter. Now we come to the performance section here. In the performance section, we will define our panel elements as masonry wall using the masonry tool option. Here, yes, we select this option. And when we select with the mouse, yes, the program has now recognized all of them as masonry wall. It has some characteristic features. We need to enter these for the walls. So, how do we obtain these values here? Where do we get them from? Based on what do we enter them? We are entering this according to our regulations. How are these values obtained in the regulations? Now I will explain this. First of all, I would like to start here with the characteristic compressive strength of load-bearing masonry walls. So you will either obtain the FK value from the table here or through experiments, and after obtaining this value, you need to enter it into the section labeled FD in the program by dividing it by the strength reduction factor. So, what is the reduction factor for strength taken here? If the masonry unit you are using, that is, the unit you used to create the masonry wall, is gas concrete, you will take it as 1.75. If it is a different material other than gas concrete, then you should always consider it as 2. You can select your masonry unit from here. Here, for example, there is aerated concrete for demonstration purposes this way. You can choose the option you want. When you make a selection, some default values will appear Here, you need to enter the value you obtained through experiments, or the value you will obtain from the tables. So how do we obtain this value from the table first? We need to know the compressive strength of the masonry unit used. Based on this, we mark one of the values here. And of course, you need to know compressive strength of the mortar plays a role in the formation of this wall. Here, M10 represents the mortar with a compressive strength of 10 megapascals. And of course, the class of this mortar is important. Is it being used for general purposes or as a thin layer mortar? This is important. Thin layer mortar is also interdisciplinary. Masonry here is an interdisciplinary mortar layer. It is a type of mortar that ranges between 0.5 millimeters and 3 millimeters. All other types of mortar are referred to as general purpose mortar. And of course, unit class is very important here. From brick, concrete, aerated concrete, they are usually divided to Group 1 and Group 2. Here, what is meant by Group 1 and Group 2? If we look at the table above, the unit of masonry is very important here. Brick, concrete, if it's brick, then the percentage of the whole ratios here is very important. If it is less than 35%, it falls into Group 1 for brick or concrete. If it is also less than 35%, it falls into Group 1. If it is between 35% and 50%, it falls into Group 2 for both. You need to make a selection from here. For example, our masonry section is brick. And in the whole ratio, Group 1, say. Of course, if we are using general purpose mortar. Here, let's say for Group 1, we are using general purpose mortar, or mortar compressive strength, is M10. That means, if it is not Group 1, the importance of the natural thing here does not matter. Since it directly gives the group number, it does not matter whether it is brick or concrete. For thin layer mortar, these are important. Let's say it has a compressive strength of 10 megapascals. 10. The unit compressive strength of masonry is also 15. Here you are reading the table. A value between 7.3 and 9 comes out, so a value within this range. You can consider it as the characteristic compressive strength FK value in megapascals. This is how the FK is calculated also in the relevant table. So precisely, the program also includes FB0 value and the FB0 value as well. We will obtain a different result in this. Yes, by FB0, you mean characteristic initial shear strength. FBK is the characteristic shear strength of the wall. Program requires the input of the FB0 value to calculate the FB. Here we will either find the FB0 value, which is the characteristic initial shear strength from the table, or determine it through experiments. Here, the masonry unit is very important. Brick, concrete, or aerated concrete. You will choose this. After selecting, you will determine the type of your mortar based on whether it is general purpose or thin layer, then determine its strength. After determining this, the coefficient next to it in megapascals. For example, if it is a brick, between M10 and M20, your compressive value for the mortar and for general purposes is 0.3. Your initial shear strength, FB0 value, is considered to be 0.3. After obtaining these values, what you need to do is fill in the table here. Besides that, we have also assigned our material. We don't have any issues at the moment. The program currently considers these panels as masonry wall. Now, there is another important point. Here, if you want, you can create openings in the panels.
Here, when you reach the opening section, you can create openings, such as windows and doors. There are only some important rules here. For example, it is not allowed to approach the edge of the wall by more than 1 meter. According to the regulation, there must be at least a 1 meter distance. We can find these in detail in such rules and design standards. When we come to the design standards here, we click on the masonry building option that we need. When we click on it here, in this section regarding the masonry wall construction, there are a few options available. These are very important options. First of all, there is an option for minimum size control of the wall here. It is beneficial to check this. When we check this, the size control seen here is performed by the program. What does the size control here tell us? It actually explains the situation I mentioned earlier. Here, if our earthquake value is greater than 0.5, the distance of the openings in the masonry wall from the edge must be greater than 1.5 meters. We can consider a window opening here. Here, this open part is also a window opening, and these in between our masonry walls. In the masonry wall, we have an opening, which is our window opening. The distance of this window opening to the edge, if our earthquake value is over 0.5, it needs to be over 1.5. If it is less than 0.5, it needs to be over 1. In the middle, if there is a section between two window openings, then there. If it is greater than 0.5, earthquake value needs to be greater than 1. If it is less than 0.5, needs to be greater than 0.8. This is important. The friction coefficient is in question here. The friction coefficient here was variable in the 2007 regulation. It could take different values, therefore, it has been included here as an option. However, in our current regulation, this is already fixed due to the formulation, and is our 0.4 FVK formula, our 4 FVK formula. Therefore, there is no need to touch it here. It has automatically been taken as 0.4. It can continue this way. Here. And we have one more very important option. It applies to openings smaller than 1 meter. Applicable for wall openings, in other words. The option here compares the excessive rigidity increase caused by openings smaller than 1 meter with the full capacity rigidity. When we click this option, it prevents obtaining a value greater than the rigidity of the fully filled wall. Therefore, this is definitely an important option. The fixed height option can be selected for the 2018 regulation. Normally, in the 2007 regulation, the smallest height resulting from the openings in this wall was taken into account. Therefore, this option was chosen. We can already consider 2018 regulation in this way. However, due to the resulting openings, it is also beneficial to mark the wall piece option here. This way, the walls are considered piece by piece. In this regard, it is an important option. This option and this option definitely need to be marked. And as I mentioned here, the fixed height option may already be selected for the 2018 regulation. There is no problem here. Normally, this option was checked in the 2007 regulation, so these openings occur. The calculations took into account the lowest, smallest wall height next to the openings. Yes, this is generally how it is. I can say that. There are some important options.
Now, when modeling a masonry building, these types of structures are modeled with panels, as I mentioned, and our panels here are unreinforced panels. Since there is no reinforcement here, these cannot be designed to be highly ductile. Now, they cannot be designed to be highly ductile, and their performance during earthquakes is not very good, due to poor behavior under earthquakes. An inadequate load transfer between walls in such structures. Load transfer between the relevant shear walls is facilitated by horizontal ties, and since it adds rigidity to the relevant masonry wall, all relevant walls are modeled with horizontal ties around them. Its modeling somewhat strengthens its performance during an earthquake. We can also achieve this in the program. So, how are we going to do this? First, we go to the floor arrangement. Here, we select the masonry wall option, and we check all of them. Then, here we come to the general changes section, and here, to the part indicated by do. We are entering our horizontal tie height. Here, I am setting this value to 40 centimeters, and as you can see, a horizontal tie has been assigned to all of them. The horizontal tie is very important, as it not only adds rigidity to the structure, but also encircles it. There is also a vertical tie. When a vertical tie is added, the building's earthquake performance is further improved. The building's earthquake performance is healthier compared to normal unreinforced masonry buildings, and they are more resistant to earthquakes. In our regulations, these types of masonry wall are referred to as confined masonry wall. In normal, classic, unreinforced masonry wall structures, as seen here, there is a horizontal tie, but no vertical tie. If a vertical tie is also added here, then we can call it a confined masonry wall. There are some rules related to this in our regulations. When we add a vertical tie to a structure, the maximum distance between two vertical ties should be 4 meters, and the vertical ties added to a single wall are spaced at intervals of 4 meters. However, there is also a limit to this. A single wall should not exceed 16 meters in length. We cannot add another vertical tie here, because the exact distances are 4 meters and up to 16 meters to the boundary. So 3 vertical ties have been added beyond that. We cannot add more vertical ties within a single wall. This is important. Additionally, according to the regulations, the wall lengths L1, L2, and L3, which are not supported here, must be less than 5.5 meters, depending on our earthquake design class. If our earthquake design class is 1, 1A, 2, or 2A, and if it is 3, 3A, 4, or 4A, then it can be designed up to 7.5A. In that case, the situation is a bit more relaxed. According to your earthquake design class, this limit exists, and if you exceed this limit, let's say it exceeded 5.5 meters and became 6 meters, we need to place the vertical ties here so that they are no more than 4 meters apart. This is very important. Let's say this is 10 meters. In that case, we will cut and place 2 vertical ties
They need to be placed so that there are at most 4 meters between them. If these distances are not exceeded, vertical tie is actually not necessary. However, vertical ties are not only used in these situations. The items in which these are generally used can be summarized as follows. Here, at the free edges of masonry walls, that is, masonry walls, on both sides of wall openings larger than 1.5 meters in area. And as we mentioned earlier, the distance between errors in every 4 meters of wall length should not exceed 4 meters. And finally, at the junctions of 2 load-bearing walls, if the nearest vertical tie is more than 1.5 meters away, it is necessary to use a vertical tie at the junctions of the 2 load-bearing walls. In such cases, this is important. Here, of course, we are talking about confined masonry buildings, where the cross-sectional heights and reinforcement values for vertical ties are provided. Attention needs to be paid to these. The cross-sectional height will not be less than 30 centimeters in these cases, of course. The longitudinal reinforcement is 6 to 12. The reinforcement should be spaced no less than 8 to 15 centimeters apart. When modeling the vertical tie, its cross-sectional width should, of course, be at least as thick as the wall. Generally, these are the rules I can mention. In relation to these, when we came to the program, horizontal tie modeling was done. So, how will vertical tie modeling be done? Vertical tie modeling is actually done using columns, just like the normal column models you are familiar with. Only this column is assigned a different material. We are completing our vertical tie model. Again, we will go to the performance section and assign the E3 material to the relevant column we defined earlier. And of course, since vertical tie is a reinforced concrete material, we will select the reinforced concrete option here. In that way, we will have completed the material assignment. And of course, the concrete values and reinforcement need to be entered here as well. The characteristic yield strength value of the reinforcement is determined in this way. Before we move on, I need to mention one more important material property related to the masonry wall. Here you can see that when we enter the FB value, the Elastica module value changes automatically. Yes, look here. The Elastica module has automatically changed if it is not determined by experiments. The regulation states that you can take the Elastica module as 750 FK. Here, since my FD value is 20, I divide it by the strength reduction factor. So, I divide it by 2. Of course, the gas coefficient is 1.75, so when I enter 20 for FDA, the program understands that FK is 40, and it automatically multiplies this by 750 and writes this value for me. Of course, you can change this manually if you wish. However, if it is not specified by the regulation, it is taken as 750 times the FK value, and in this way, it is automatically determined. Now, to enter the vertical ties, I will perform a column definition here. I am defining the column. For example purposes, I will only define it in this region. Yes, we defined it, and here it is. I will perform the material assignment. Yes, E3. I took the without reinforcement like this. The other concrete is like this. Yes, I have now completed the E3 material assignment. Yes, here I have shown the vertical tie modeling for demonstration purposes. Here you need to assign vertical ties to the necessary points in your project, according to the regulation rules. and as seen in the selection of the R-value. In masonry walls, the R-value can be taken as 3. In confined masonry walls, and the other D-value is taken as 2. Here, our earthquake class is 3. More precisely, our earthquake design class is 3, as stated here. In our building usage class, it is 3, and in our building occupancy class, it is a single-story building, 8. Here, we considered the R-value as 3. We also took the D-value as 2 if we want to check these from the regulation. Here, we need to move on to the 4th section. Yes. Yes. The R-values for masonry wall are here. For masonry wall without reinforcement, the R-value is taken as 2.5, and the D-value is taken as 1.5. For the confined masonry wall, that is, the masonry wall in our example, the R-value is taken as 3 and the D-value is taken as 2. Here, since the behavior of the confined masonry wall against earthquake is better compared to the structure of the masonry wall without reinforcement, the R-value can be taken as 3. However, the situation here is worse in terms of earthquake resistance. To stay on the safe side, a smaller R-value is used here. In other words, the earthquake values here are applied to the structure as slightly larger. This is important additionally. In these two options, the building class can only be modeled as 8. So here, the height is restricted by the regulation. Similarly, in reinforced mesh-ner wall structures, they're natural. Flexibility level is also high. There, building slope class 7 is also allowed, but only one of 7 or 8 can be used. Here, only 8 is allowed. Since there are no very safe structures during an earthquake, the regulation tries to stay on the safe side by keeping the design, specifically the height, of the relevant structures very low during the design phase. It does not allow very tall structures for the modeling of the issues. Lastly, there is one more point related to modeling that I need to discuss. It is as follows. In masonry wall structures, walls should not rest on the slab. A beam must be defined under the walls. Here, we already have a single-story structure, and there is no situation where any wall rests on the slab. However, we need to be very careful with this type of modeling. We can also do more than one floor. In such cases, it is necessary to define a beam under the walls. Related to this, in our macro menu, there is a macro at the bottom option called Masonry Wall 6 Static Model Control. When you click on this macro, if you have a masonry wall structure resting on the slab, the program automatically defines a beam for Masonry Wall 6. And in this way, any negative modeling is avoided. It is absolutely necessary to place a beam under the walls. This is an important option. Yes, in general, these are my remarks regarding masonry wall modeling. Thank you very much for listening to me. I wish everyone good work.